Hi everyone, today I want to share with you how to validate your Flox alleles. Making sure that your Flox allele is working as intended is critical to having reliable in vivo results. A defective Flox allele can delay your project for months, if not years. In the next 5 minutes or so, I will show you the tools to test your Flox allele from your founder to your experimental animals. Before we begin, let's clarify what a Flox allele is and go through the simple notation that we are going to use in this video. We have our allele wild type with one exon here, intron, second exon, third exon, and so on and so forth. This we are calling our wild type allele. Now our Flox allele will look pretty much the same. So we'll have our exon 1, intron. The difference is now we are going to have these logs beside, typically flanking one of the exons, and we are going to call this allele flank by logs besides allele. There's the Flox, where is the Flox coming from? And finally, what we want to do with these Flox alleles is remove this bit in between to generate a null allele that will give us a deficient protein. If we have exon 1 here flanked by this Flox allele, then these two will come together, everything in the middle will go away, and we will end up with the exon 3 after exon 1 and only one LOXP site. And this is our null allele. With that out of the way, we can move to the different strategies to validate the allele. But before, we need to understand how the alleles are generated so that we know what can go wrong and what to look for. Very good. So how are Flox alleles made? And we are assuming here that we are using a modern CRISPR strategy where we are adding two independent LOXP sites. So we will have our exon 1 followed by exon 2 followed by exon 3 in our wild type allele. And what we are going to do is use a sgRNA targeting somewhere here in the intron to insert one LOXP site, and we are going to use a second LOXP site targeting this intro to insert the second LOXP site. Then we are going to throw into the cell this synthetic template that will span intron 1 or part of intron 1, and we are going to add here the LOXP site, and the same we are going to do for this other LOXP site. We have this template here, template, and what is going to happen when we have this mix inside the cell, there will be a cut here, then the cell will want to repair this thing, so it will use this thing, this template, as a template, therefore its name, to repair the damage generation, and that is be done with two crossovers. So the DNA will come here, then we'll go to the template, and then we'll go back to the genomic DNA. And the same will happen on this other side after the cut. So this type of repair is called homology-directed repair, and that is what we want in this case. So if this goes fine, then we will end up with the Flox allele, where we have exon 1, and then we have the LOXP site and the exon 2. And if everything goes well on this side as well, we have the exon 2, exon 3, and this is our Flox allele. So this is how in theory it should work, but things can go wrong, and let's see what are some common problems that we can check for. Right, so what can go wrong? What can go wrong? The first thing that can happen is like we don't have any cut here. So for whatever reason, that probe didn't cut. It's rare, but it can happen. So in this case, we'll have like exon 1, exon 2, nothing happened here. And then there is recombination here, and only one of the Flox is added, but here there was no cut. So this is something we can look for. The other thing is that there is cut, but that there is the NDR, so there is no recombination, and what happens is a non-homologous end joining. This is another type of DNA repair, And imagine that this happens on this side. So on the first one, everything went fine. We'll have the LOXP side, then the exon 2. But here there will be some repair where some DNA damage is made, and we don't have exactly the same copy of DNA as we had before because this type of the repair is defective. This is non-homologous end joining. And then the third thing is that we are targeting these templates here, but actually you can have cuts in some other places of the genome, and these templates can insert in some other regions as well. So we have to account for the possibility of an ectopic insertion, and by ectopic I mean somewhere else other than this locus. So in that case, instead of this template being inserted in gene that has 1, 2, 3, this is inserted in another gene with exon A, and then you have exon B, and then you have exon C and D, and you have a LOXP site somewhere here, completely different locus to the one that we are looking at. So this, we will call it ectopic insertion. So the first animal that you will be able to test is your founder. The main goal here is to determine if you have insertion of the LOXP sites in their correct locus. Here is what you need to do. So now we are testing our founder for proper insertion. We will have our exon 1, and this part will be coming from the genome. But after this can potentially come from the template, the last part of the exon, by the way we designed our strategy, and the same like this little bit of the exon 2, and we will have our LOXP site, and with our strategy the same will happen with exon 2. So the key here is to test whether this insertion happened actually in this part of the genome, and to do that we use a PCR where we have a primer that we are using outside the homology arm, and this is what we are calling the homology arms here, and the other one we will use the reverse primer downstream this LOXP site here. And if we have product, it means that this recombination happened in the desired locus. And the same we'll do for the other LOXP site, but for the moment we'll focus on this one. If everything goes fine, we will have a situation where we have the amplification of this part of the genome that is followed by the amplification of this other part of the template, which includes the LOXP site. So this is what we expect for our Flox allele, but there can be situations where instead of having that LOXP site there, we can end up with nothing at all. And this can be because, as we discussed before, there was either no cut or there was a non-homologous enjoining. And here what we are amplifying is only the other wild type allele, or it could be also like an ectopic insertion and this locus remains intact, so we have the same as the no cut. There is still another possibility where we have like the part of the exon 1 and then we have a much shorter version of this amplification, and this could be because we either have a non-homologous enjoining, so there was some sort of damage generated here that make the allele a little bit shorter. So these are all situations that we can look at. Right, once you validated your founder, the next things you want to verify is that you can actually generate the null allele. Here is what you need to do. So what we want to do here is to create the null allele. So you will have your founder and you probably want to cross it and generate an F1, and then you will take an F1 animal that is homozygous for your Flox allele, and you will cross it to an animal that will be of course wild type for that allele of interest, but will be positive for a CRI recombinase. CMV CRI is a type of CRI that is used here because it's expressed in the embryo and deletes the allele in all the animal. So once you cross these two animals, you will have 4 possible combinations of genotype. So imagine we have here a male, have a female, and another male here, and a female. So we can either have for our gene of interest that the animals are wild type Flox or wild type, and this can happen irrespective of the sex. And let me explain in a second why I put null here. So, and the animals can either inherit or not inherit the CRI. So if it doesn't inherit the CRI, the Flox allele will remain as it is. Again, if we don't inherit the CRI and is wild type, nothing will happen anyway. So in those two cases, we can have a CRI without altering the genotype. But when we have the presence of the CRI and the Flox allele, this Flox allele will be actually converted into the null. And that is what we want to see happening for this. So now that we have that animals, we can validate the recombined allele in the same way that we validated the Flox allele. So again, we will have our exon 1, we will have our exon 2, and we have our exon 3 here, and we will have our log sites. If we actually get the null allele, then we will have exon 1, a little bit of the exon 1, first Flox allele, the first Flox site, and then skip the exon 2, we move to the third, and this is the other part of the genome. So in the same way that we tested our log site, we will test the null with a primer that is outside the homology region and another primer coming from the opposite direction that is downstream this log site, and we do the same from the other side. Then we validate that actually this amplicon can be generated, and that will indicate that actually we not only have the null allele, but it's also in the correct locus. So now that we know that we have a functional Flox allele, the next thing to do is to check the Mendelian inheritance of that allele to be sure that everything you see is happening in the expected locus and there is no other ectopic insertion somewhere else in the genome. So we will do the testing of the Mendelian inheritance, in this case of our Flox allele. So you will cross your founder to the F1, and then the F1 you will cross it again with black 6 animals, and at a certain point you will have a couple of quite distantly related heterozygous animals for your Flox. So you will cross these two, and here you are expecting 3 types of phenotypes. Here the sex doesn't matter, could be anything, but you typically have 1/4 of the animals being wild type, then half of the animals being heterozygous for the wild type and the Flox, and then 1/4 should be Flox. So this is what we want to see, and we want to see this in a 1/4 situation. This is quite good. Something that can happen, however, is that you never get that situation, and it doesn't matter what, you always get a wild type allele. And this means that you cannot get rid of the wild type allele, so maybe this is because the Flox allele is inserted somewhere else, and therefore you will always inherit a wild type allele, even from the mutants, because the Flox allele is not where you think it is. So in this case is not great, but if you get these results in the first liter, you need to continue looking at more liters to have enough numbers and be confident actually that this 1/4 is not happening. So let's assume that your Flox allele is coming up at the expected Mendelian ratios and everything has been validated, so far has worked. Finally, you have to do a similar analysis for the null allele, and in this case we will put the emphasis not so much in the Mendelian inheritance but on the expression of the protein. So here we are going to test for protein expression in the nulls. So in this case, as for the heterozygous Flox, you will have like 2 or 3 crosses so that you can have a cross between plus and null animals that are not very closely related, just to avoid inbreeding, and check the video of inbreeding if you want to learn more about that. And in this case, again, you can have 3 types of phenotypes irrespective of the sex of the animals here, and in 1/4 of the cases you will have wild type, then in half of the cases Here we have the heterozygous, but the null is a completely different story, and this can range from 0 to 1/4, and this ratio will of course affect these other ratios over here. So if your animal is embryonic lethal, you will not have any pups, but if you do have some lethality and you do have some live animals, what you can do is to take those animals, and what you want to do is to do a Western blot from these animals so that you can see actually that the protein levels of your targeted proteins are gone, and that will be the ultimate proof that your null allele is actually a null allele and that you are depleting your protein of interest. Well, that's it for today. If you like the content, please subscribe to the channel. It will make these videos more accessible to people like you, including yourself in the future, and I will see you then in the next video.